Hello everyone, my name is Angel Yang, a graduate student in chemical engineering at Stanford. And today I will be talking about our project, which is to identify material composition with computer vision. The motivation of this project is that as a grad student in chemical engineering, we have extensive needs of processing the images taken from transmission electron microscope, which is a very powerful tool in capturing the details of nanomaterials. A classic TEM image looks like that. It's a grayscale picture. In material science, we're especially interested in knowing the distribution of elements on such image, which always requires very extensive technology. And however, our research group is a very heavy TEM user. Therefore, in the past several years, we have built a huge data set of such images, which is able to help us build a model for some classification task, first of all. And after we gain insights into the classification, we hope to build such elemental analysis map by using this model. Let's now look at our data set. There are 10 different classes representing 10 different materials in the dataset. The position on the periodic table are marked here. You can see that as the element becomes larger or heavier, the colors tend to be darker on the image. There are up to 5,000 images taken from 6 microscopists in our group. And because we want to enlarge the dataset, we have divided them into 4 different areas and eventually reached 20,000 images. And from the left-hand side figure, you can see the classes are not well balanced. So later we'll also implement data augmentation to try to achieve balanced groups. After several trials, we have set to use transfer learning, which is to take one of the well-established model from Google, Inception V3, use one of the layer mixed 7 because it contains enough feature for us to train. And we added 3 additional layers for us to output what we want. So our input will be a raw TEM image, and then our output will be predict which class it belongs to. Here is the baseline result. Here we, without any data augmentation, and by using just a regular cross-entropy as our loss function, we achieved up to 60% in accuracy. In the confusion matrix, you can see that most of the images are classified into the largest classes, which is not surprising because of the unbalanced data set. So in order to deal with the unbalanced class problem, we have replaced our loss function into a class penalized loss function, which is to introduce a weight here. So with that, we are able to penalize the misprediction for smaller classes more. And the accuracy now is set to 71%. And finally, we have used data augmentation as well to try to balance each of the group. And with this augmentation, we are able to reach 83% accuracy. In the confusion matrix, you can see that almost every of the image are classified correctly. There's still one group though, magnesium oxide still has a relatively low accuracy, which is probably due to the fact that this group has a lot of features also shared by other groups. Now we are also interested in knowing how our model compares with so-called human experts, who are the PhD students and postdocs in our research group. So we feed them 50 unlabeled images in the validation set, and they are able to achieve up to 63% accuracy. Compared to the confusion matrix, you can see that the class that tend to mispredict also confuse our model for the most. However, with a higher accuracy achieved by our model, it means that our model is able to detect the features that is hard to be detected by the human. So with that, we have built a model that is able to help us achieve 83% accuracy in classify common materials. Now we are also in a process of building a class activation map, which is help us to know how the model knows the location for different elements. Hopefully using that, we can build the elemental map in the future. Thank you.